assessment. All right. Hi, everybody. My name is Sophia, and I'm a graduate student at Georgia Tech, and I come from the Trinity collaboration. And today I'm going to be sharing some first analysis from the Trinity Demonstrator. So as we learned from David, we use Earth skimming for PeV to EeV energy range tau neutrinos to be able to detect them via the air showers that they produce in the Cherenkov radiation. So we have a imaging atmospheric Cherenkov telescope that points at the horizon to be able to see the air showers, and we keep it on the mountain because that's the only way that we're going to be able to maximize our acceptance. So we have 3 different phases for Trinity, as again we learned. So we have the demonstrator, Trinity 1, and the full observatory. And with each phase of the of Trinity, we're going to have an increase in sensitivity of over an order of magnitude. The Trinity demonstrator's main purpose is to serve as looking into the background that goes on at this, when we're looking at the horizon, because we talked about how we have, when you point up with the gamma ray telescopes and such for imaging air showers, you get cosmic ray and such, but we need to understand what's going on within our background and make sure that we don't have any unexpected sources of background. We also need to establish our analysis, which I've been working on, and then the simulation chain, and of course, setting up our operations. So Trinity Demonstrator is currently operating, and it has a small field of view with a 256 pixel camera, a angular resolution of 0.24, and a mirror area of a little over a square meter. We began our commissioning and our first light in October of 2023, where we had a 1-year commissioning period where we began our operations, we calibrated our trigger, we worked on our signal calibrations, and aligned our optics. And one way that we can tell qualitatively that we have good optic alignment of our mirrors, as you can see demonstrated in this here, we have to make sure that they all point on the camera. We have the image at sunset of the horizon onto the silicon PMs. So we actually have a little portion of our camera that's above the horizon, and the majority of our camera is below the horizon. And you can see a clear line in no fuzziness between the tops of mountain peaks and the sky, which means that we have a good optical alignment so that any light is going to be within our pixels. And then what we have here is we wanted to ensure that when we were commissioning our instrument, we were able to see Cherenkov radiation as expected. So we tilted our telescope up for one time only, and we went and we saw a cosmic ray air shower. This is uncalibrated. We did nothing else with it besides saying, can we see what we're expecting to see? Our camera triggers on any single pixel that goes above 20 photoelectrons, and this gives us an average trigger rate of 0.5 hertz. And what this image here is showing is our typical event display for our camera, where we have the sky on this bottom portion. The ground that we're going to see is all of this here, and then a single pixel that came above that 20 photoelectron threshold, and the rest of the pixels are having a low number of photoelectrons. These are the typical type of events that we see, but we have some more interesting events that we're going to talk about. So for our data set, we began the analysis on a period between October 2024 and June 2025, and we're still collecting data at this time, so this is not done. But for everything that we need to do, we have 346 hours of our best nights of data. We are affected by time and weather, so we have more data to look through. However, this is what we're going to begin our analysis with, and we come out with around 1 million triggered events. So when we have this many events, we need to be able to sort through and remove events that don't contain Cherenkov radiation. And to do that, we do an image cleaning. And this is pretty typical for gamma ray telescopes. And we employ that here as well. So what I have here is a single simulated event from our Monte Carlo simulations. And this is what we would consider a gold-plated event. This simulation came from a 400 or so PeV neutrino that had a distance from the telescope of 170 kilometers and an emergence angle of a little over under 2 degrees. And what we're seeing in this image here is the number of photons that hit the camera plane in our simulations. And then this image on this side is showing the expected camera response that we would see if we had actually captured this image with our data. And you'll notice we have two different types of scales. We have photons and we have photoelectrons. Photoelectrons is the actual response that we receive within our telescope. And we have a saturation at 160 photoelectrons with the current way that we operate our telescope. So that's why you see all of these pixels coming up as yellow. To then, within each event that we have, remove the pixels that we don't think contain Cherenkov radiation, we do a core and boundary pixel selection that is also typical in gamma ray telescopes for air showers. And core pixels are selected by being the pixels that have some sort of a dynamic range of the triggered event or triggered pixel and are connected to that triggered pixel. So that's what you see highlighted in black in each of these. And then we have boundary pixels that are going to be within 30% or so of the maximum core pixel and within a singular ring of pixels around a core pixel. And that's what you see here again highlighted in black. And now we have our final cleaned event that we will use and do our event selection on to understand what kind of events that we have surviving from our data set. So we parameterize our events with two different parameterizations, size and image pixels. Image pixels are the number of pixels in the cleaned image, and the size is the sum of the photoelectrons in all of those image pixels. So for that gold-plated event that we saw and we cleaned already, we have a size of 2,500 or so photoelectrons and image pixels of 18. Now we can compare that with our actual data, that 346 hours of data. We end up with 500 or so events, gives us a rate of about an event per hour or so. The majority of our data does not look anything like these air shower events that we saw with this gold-plated simulated event. We have two events here, but as we go through, I think I will be able to convince you that they're not air showers. So we have four different types of events that we see pop up: muon tracks, electronic, fuzzy, and spillover. So let's start with muon tracks. Muon tracks are going to be distinguished by having a singular line through the telescope with very little spillover of photoelectrons into other pixels. This is not realistic to what an air shower actually looks like. You would expect some sort of spread. And I highlighted this one with a star here because this is one of the events that had the same image pixels and size as our air shower event, but it doesn't look like it. We also did a study on our direct muon hits to understand how these appear in our camera. So for 2 hours, we set up two plastic scintillator paddles, and whenever a muon traveled through both of them, it would send a trigger to our readout. So we would take images of muons that were triggered. And what we end up seeing is events that look very similar to the type of muon events that I showed you from our actual data. And this is good. This means that we think we know what came, and those muon events are muon events. Typically, these are rare muon events where we have these very long very large amount of pixels. Most muon events are going to have like 2, 3. We're also doing some more studies with our door closed to ensure that we are seeing the same rate of muon events as we're seeing in our data set, as we haven't done that. Next, we have these spillover events. These events are pretty frequent, or not super frequent, sorry. They're not as frequent. They're around one event every 23 hours. And they cannot be characterized by a single line, like a single muon going through our camera. However, they don't really share the same image shape as our gold-plated event that I have highlighted. And we're not exactly sure what causes these types of events. We've talked about it a lot between the collaboration, and one of the ideas we have is this comes from a muon and an electron interacting and allowing that spillover into these other pixels. And one more thing I would just like to add, right? These two events here, these two, they're very close to the sky, which is not really what we're expecting for an upward going air shower event, which is another reason that we don't think that this is going to be an atmospheric air shower event from a tau neutrino. We have these fuzzy events as well. These are the ones that we don't understand really at all. We need to look into them more. There's only 2 of these events out of so it's every 173 hours we expect to see one of these events. They don't share the type of topology we're expecting for these gold-plated air shower events. So we're going to look into this more. And the reason I started this one again is this is the other event that looks at a similar number of image pixels and size, but they don't look anything alike. And again, these happen very close to the horizon. Lastly, we have these electronic events, and I don't classify these over the number of hours that we expect these events because they were very concentrated to particular days. And this just came down to some sort of malfunction or some sort of weird glitch that happens when you have a experiment that you work on. And then it just magically starts and fixes itself. So what we expect happened was each of these matrices of silicon PMs are in batches of 16, as you can see here, and that's what you see in those red grids. And they're all connected by this board called a SIAB. And so they're all electronically connected. And there's times that if one pixel fires, all of the other pixels in that silicon PM will fire as well. And they'll create events that look like this. These are not realistic. So what we end up having is no events that we end up seeing here that match the air shower events that we're looking for. And particularly with muon tracks, they're very common in our data for these for surviving our image cleaning. However, in future experiments, we can permanently install scintillator paddles that if a muon goes through our camera, we can then add a flag to our readout to ensure that when we do our data analysis in the future, we can just immediately put those events to the side. And if we wanted to do something else with them, we could, or just reject them. And then these other these other fuzzy and spillover, they just don't look like the air showers that we're expecting. So we're happy as of right now to say that we don't have any unexpected backgrounds, which is great for moving forward with our next experiment. However, we do understand that we still have more data to look through, and we need to just ensure that optimistically, we don't see anything else. And then in the future, we have to complete our Monte Carlo chain to simulate our acceptance, calculate our limit on diffuse neutrino flux, even though it won't be super competitive, and of course, look towards Trinity 1. So thank you.
Thank you, Sophia. Is there a quick question? Okay, maybe a very quick one.
Okay, so when I see demonstration picture of how this telescope work, I see they only show tau neutrino. Is it only sensitive to tau neutrino?
That's correct.
Yeah.
So because of the interaction of the tau neutrino in Earth's crust, we expect the tau to decay somewhere in the lower atmosphere. Electrons will decay immediately within Earth's crust, and muons will go beyond the lower atmosphere. So we only are sensitive to taus.
Okay, so let's thank Sophia again.